Hi, welcome everyone. Welcome to this course, An Introduction to Statistical Mechanics in Soft and Active Matter Systems. So, in the last lecture, we were talking about different stochastic processes, and we talked about Markov processes, and we have seen that what are those properties that Markov processes follow, and also we uh, derived the Smoluchowski equations so that we can get the differential equations, the partial differential equations when there is some drift in this, and we also got to know about uh, two fixed laws like fixed first law and fixed second law, and we stopped in the like discussing Markov processes and stationary processes. So now today we will continue our discussions from there. Okay, so let me share my screen. Just a minute. Okay. Okay, so we first define the joint probabilities for different cases, and then we you know last talked about what are those stationary processes, which is we sort of calculate. Okay, so today let me start my discussion here. So basically today I will start my discussion from the master equation. So these master equations is very much important whenever you talk to whenever you study this kind of stochastic processes. So the master equation. Okay, so now the conditional probability of a Markov process that satisfies a certain equation which is called the master equation. So we'll start from there. Okay. Okay. So an equation satisfied by the conditional probability P of KTJ. Now to start the discussions of this derivation is the Chapman-Kolmogorov equation which is satisfied this master equation. So starting point for the derivation of this equation which is master equation is the Chapman Kolmogorov equation satisfied by the Markov processes. Okay. So what is that? That is precisely is P kt j, this conditional probability, is equal to 1 to n p of k t minus t prime starting from L and p L t prime given that j for any t prime belongs to 0 to t. So what does this equation say? Let's understand this point. Okay, so this equation says, let's say this is equation number 1. The probability, let's interpretation. So interpretation of this equation is the probability of propagating from an initial state, let's say which is j, to a final state k is the product of two probabilities, which are the probabilities of propagating from j to any intermediate state L, and subsequently from L to k, where you are taking summation of over all possible intermediate states, which is summed over all possible intermediate states. So basically, let's say you are at this state which is j, and you need to reach here which is k, which is at t, which is at 0. So to reach here you can go in different paths So these are different values of L, and this at this point. So you can take this kind of states which are like all possible states can happen in this scenario. Now you understand this point. So basically what we will do here, we will sum over all possible states in this region. Okay. So but the important point is this equation 1, this Chapman-Kolmogorov equation satisfied by the Markov processes, this equation 1 is a necessary is a necessary but not sufficient condition, not sufficient condition for a random process to be Markovian, to be Markovian. Okay. So there is a common misconception that this is unique to Markov processes, but this is not unique to Markov processes. So this is not unique to Markov processes. So it is actually, it is an identity, it is an identity which is called a so-called renewal equation, renewal equation renewal equation that is actually satisfied by a more general family of stochastic processes. Now here we are only talking about Markov processes. So we will talk about that. Now let's see these things. Look carefully that this Chapman-Kolmogorov equation is a nonlinear equation because there is a product of two probabilities. So that the Chapman-Kolmogorov equation is a nonlinear equation for the conditional probability. Conditional probability. Why? Because since the right hand side of the equation is quadratic in P, right? Now nonlinear equations are pretty much harder to solve. Okay, so we need to use a certain tricks to make this equation linear. Okay, so what we will do here, we will do by defining a transition probability per unit time. So now we can make the equation linear by defining a transition probability per unit time or transition rate, which is, let's say, so between, so this transition rate is this quantity which is between any two distinct states J and K. Now we also know that we also know that for a stationary process, process the probability follows this form. Let's say k t plus delta t from j of t, that becomes p of k delta t is equal to j. So time translational invariance, right? So that's the case, then we can now assume that in any infinitesimal time interval delta t, the probability p of k d delta t of j is proportional to what is this time interval, right? Now you can choose a proportionality constant, that would be the transition rate, right, with a coefficient of proportionality proportionality that depends on J and K, which makes P of K delta T at J is W of K from transition rate times T. So as this interval increases, the probability also increases. So where J is not equal to K. So that we can write, right? Because that is what is the transition rate. Okay. Now these relations looks very pedantic, but it's not that much pedantic, because all Markov processes is not, for all Markov processes this is not guaranteed, right? So basically we will now see that how this transition rates uh, you know you know sort of gives this probability evolution. Okay, so for that we will now if uh, so for a Markov process it is not always guaranteed, but when it is guaranteed, when it holds good, it defines the transitions rate. So equation 3 equation 3 doesn't always hold good for any Markov processes, but when it does, when it does, it defines transition rate, which is this fellow W K, given that is it starts from J. Now this quantity Wkj is actually the probability per unit time that the random variable jumps from, let's say, state or its value in J from its value K, right? So this quantity actually says the quantity the quantity Wk of J is the probability per unit time, probability per unit time that the random variable jumps from its value in the state J to its value in the state K. in the state K. Now if you write this way, then you can sort of define that that let's say if you take the difference of these two quantities, then this will make the differential equation for the set of conditional probabilities. Okay, how? Because you can write here like this. So basically if you take negative minus, and if you write like this, then if you say this, you can write, you can this equation you can write the equation 1 as, which is ddt of p kt of j is equal to sum over L equal to 1, L not equal to k n W of k by L p L p p at L for given time t into j. So basically you get this for this. Basically you get this, you can write the equation number 1 as like this, minus W at transition rate from k to L p kt j this. So basically if you like, if you talk about this, this can be seen like this, that let's say you are taking what is the probability rate per unit time, how it is changing. Let's say this state is k. Okay, so this will be how many paths coming into this and how many paths coming out of this. So let me take this, how many paths coming out of this. So this is written by this. So this term is like, what is the transition rate? Like, it is like this is like the transition rate from any other state to kth state times with the associated probability, and this is transition rate from kth state to any other state, kth state to any other state. That's why this minus sign with associated probabilities. Okay, so now you will get this equation. Now for each initial state j, this should be satisfied. Okay, so for every, now it is also satisfied from this thing, and the initial conditions for this, the initial condition for this is p of k0 with initial condition j is delta jk. So that is equation number 5. Okay, now this equation is called master equation for a discrete Markov process. This equation four is called the master equation for a discrete Markov process. Now this is, you can say, this is sort of a rate equations that we sort of familiar with our nuclear physics or any kind of decay in class 12, this thing. Now one prominent or poignant question is, why are Markov processes so important at all? Why should we study that? So why are Markov processes are important? Now observe that master equation, first thing, master equation for the conditional probability, for the conditional probability distribution is a first order differential equation. Differential equation. Okay, this is a first order differential equation in the time variable. In the time variable. Now, which is actually a direct consequence of Markovian nature of the random process. So, which is actually direct consequence of the Markovian nature of the random process. Now, the solution of these equations actually requires a single piece of information, which is we need to specify the initial distribution of these things. So we only need the sole piece of information, which is initial distribution p k initial from J. Now no other history is required as usual from the Markovian process. Now this is actually what is we know at holds for deterministic dynamics, right, for both for the classical and quantum cases, because in classical dynamics Hamilton's equations for the variable in the phase space which we write, they are also first order differential equation in T, and in quantum mechanics also Schrodinger's equation of equation for the state vector, or like the you know that wave function we write, or the Liouville equation for the density matrix, they are all the first order differential equation. So in that sense the master equation for a Markov process is the stochastic analog of the fundamental equations of deterministic dynamics. So here we can comment that master equation for a Markov process is the stochastic analog of the fundamental equations of deterministic dynamics. Now we will get the formal solution of master equations. So let us say formal solution for master equation. So first assume let P of T is a column vector. We all know we can substitute a matrix like 1D matrix as a vector, column vector whose kth row is P of kt j. Now here in this notation initial state is not explicit, but we can see that how to maneuver over it. Now master equation is actually the time evolution equation for conditional probabilities. Okay, so now from here, from this equation 4 you can easily write from equation 4 you can write dp dt is equal to wp. So here since P is matrix, so this W is also matrix, right? So here W is called the relaxation matrix, in different physics literatures. So if P is n, P has n elements in that column, so this will be n cross n off diagonal elements. So and this has n cross n, so this is n cross n matrix which has off diagonal elements. Okay, so now from definition, then Wkj, this will be, from definition will be small w, which is transition rate from k to j, where k not equal to j, because we knew why this is of diagonal, because here we written that j is not equal to k, that's why all the elements are of diagonal, and the diagonal elements is wkk is equal to minus L equal to 1, L not equal to k from n WL given k. So which is W is not a symmetric matrix. Okay, now you can solve these equations. So since the elements of W does not depend on time, that means we are considering stationary process, right? That means we are considering stationary process. If that is the case, then the formal solution to the matrix differential equation will be P of t is equal to e to the power Wt given the initial condition P naught. This is equation number 9. Now where of course P0 is a column vector whose jth row is 1, and this is because of the initial conditions. All the other elements are 0. Now from the equation 9 we can get the time dependence. So from these equations we can write that the time dependence of this equation is actually probability distribution is essentially determined by the eigenvalue spectrum of the W. Okay. So basically the time dependence of the probability distribution is essentially determined by the eigenvalue spectrum of the matrix W. Now exponential of this matrix is not very easy. A convenient way to dealing with this kind of problem is to work with the Laplace transform. So a convenient way to handle to handle to handle the problem is to work with Laplace transform. Now let's do that. So let's say P tilde S is the Laplace transform of P of t. Okay. So then this equation 9 will eventually becomes equation 9 becomes P of tilde S is equal to S of I is unit vector minus W and its inverse and P of naught, let's say, which is equation number 10. So where I is n cross n unit matrix. So basically this matrix, the matrix which will be this Si minus W and its inverse this is actually, of course, the resolvent, the resolvent of transition matrix, transition matrix W. So basically what we have done here, we have replaced the problem of finding the exponential of a matrix to only finding the inverse of this quantity. Okay, so basically we have just simplified the problem. Okay, so then the known properties of this relaxation matrix will be possible, we will make it easy to something about this eigenvalue spectrum. So what are those? So let us take few cases. So let us, so, so the known properties, known properties of relaxation matrix, relaxation matrix W make possible to comment a few things about the eigenvalue problem. So we will look into this. So let us just confine ourselves to the most general statements. Okay, so what are the most general statement is sum of the all elements of W is equal to 0. Why? Because we know that one element will be like W of Kj, transition rate of Kj, because W of Kj is equal to minus W of Jk. Okay, so if you take this way, then the sum of all elements, sum of all elements of each column in W is equal to 0. So if the elements of one column is 0, so that actually says determinant of W is equal to 0, followed from the statement above. Okay, so that means 0 is an eigenvalue, 0 is an eigenvalue of this matrix. So we will come back to this physical significance of this thing later. Okay, and also the elements of W are real. and elements of W are real. So if elements of W are real, then all the eigenvalues will be occurring in complex conjugate planes. So that means all the eigenvalues will be occurring in complex conjugate pairs. Now apply Gertz-Gorin's circle theorem. To W. So then if this is the case, then these will be the contours. So the centers of the Gertz-Gorin's disks, which are formulated like this, are are located on the negative real axis of the complex plane. Now at the points where WKK is equal to minus mod of WKK, where K runs from 1 to n, where K runs from 1 to n, and the radius of the circles are given by WKK. So that means the rightmost points of all these Gertz-Gorin circle will be at this origin. That means the real part of these values will be negative except for this eigenvalue 0, because all are will be in this. So this is real part, all will be in the negative part. So hence, all the real parts of all the eigenvalues are negative except for the value 0. So except for the value 0, all will be in the negative, the real parts. Okay. That means you can easily say that time evolution part, time evolution of the probabilities of the probabilities which is governed by e to the power wt, governed by this, which is governed by this, is given by is given by decaying decaying exponentials decaying exponentials in t, and possibly multiplied by the factors which involves sinusoidal functions of t. So since it is exponentially decaying, that's why it is called relaxation matrix. So since it is decaying, that justifies the term relaxation matrix for W. Okay, now the stationary distribution. So basically, we need to ask one question, is that what distribution the conditional probability P of ktg relax as t tends to infinity, right? So it concerns actually the condition under which there exists a unique time independent distribution which we denote as, let's say, some p star or pst, where the kth row in the stationary probability pk, so there will exist that unique time independent distribution. Okay, so now if you talk about the infinite dimensional state n tends to infinity, then it becomes non-trivial. Now here, let's say we talked about the n finite and we need a unique stationary distribution. So let's say we need a unique time independent distribution PST, where whose kth row is the stationary probability P of k. So it does not depend on time. So this distribution can be given by like this: d of P of st by dt is equal to WPST needs to be 0. This is equation 11. So therefore the stationary distribution P of ST is given by the elements of the appropriately by the appropriately normalized eigenvector eigen right eigenvector of the matrix W, which corresponds to the eigenvalue 0, to the eigenvalue 0. So now we will use the explicit form. Let's say this, from the explicit form, from the explicit form of, let's say this one, equation 4, form of equation 4, then we can write this term equal to k wk by L of PL minus WL given k, Pk is equal to 0, where k runs from 1 to n. Now since we have given conditions, since determinant since determinant is 0, so we can guarantee the set of homogeneous simultaneous equations will have that unique non-trivial solutions for the ratios of the unknowns. Okay, so now let's say we will solve it for, let's say, n equal to 2 for simplest case. Let's do it for n equal to 2. So then this is called dichotomous Markov process. So here then we will get from here, so this equal to 1, so for that what we will, so mainly, so we will use two things. Okay, so basically we do not know these ratios, okay, P of 2 by P of 1. So these ratios we know, do not know, P by 3 by P by 2, and again we will use these equations that k is equal to 1 to n, all the probabilities should add up to be 1. Okay. Okay, so now let's take this thing. So basically you now get two things, that P1 by P2, P1 by P2 is W1 to 2 and W2 by 1 from that equations, and P of 1 plus P of 2 is 1, right. So from here it promptly follows that P of 1 becomes W12 divided by W12 plus W21, and P2 is equal to W21 by W12 plus W21. So these two equations follows from there. Let's say this is equation 11, this is 12, this is 13. Okay. So basically for a three-state Markov process, you can see that will be considerably difficult. Why? Because then you can have to write P of k is equal to nk by dk for k greater than 2. So let's say for n equal to 3, you will get, let's say n1 will be W12 W13 plus W13 W32 plus W12 W23. Okay, so basically let's say this is 1, this is 2, this is 3. So from here to here you get, so to reach here you can reach from here, right. Similarly you can reach from here to here. So this is W23 W12 W, and also going out of that W12 W12 W13. So basically you will get the transition probability like this. And also so like this you will get, and similarly you will get this kind of equations. So you can see that stationary distributions becoming eventually complicated, right. So you can see here. So now a similar way you have to calculate n2, n3 and so on and so forth. So basically you can see this is detailed balance. So it is evident that it is evident that the expressions get more and more complicated as n increases as n increases. But if you use a special case, then your some solutions will be simplified. So now if you use the condition of detailed balance, then each term in this equation each term in this equation they will be each term in this equation will be vanish. So will vanish. So what will become that each term in the summoned means the expressions for a one particular value of L in the summoned equation 12 vanishes by itself. Okay, so then we have W of K of L given P of L is equal to W of L of K P of K. That will be the detailed balance expression. This is called detailed balance. So for every pair of K and L. So why detailed balance conditions? So some points about it. So detailed balance conditions has its as its origin in time reversal invariance. So detailed balance means it has a time reversal invariance. Okay. And also, like, if some system is thermal equilibrium, that also talked about detailed balance. Huh? Okay. So it is also applicable it is also applicable to the to the systems in the in the state of thermal equilibrium, thermal equilibrium under normal circumstances, under normal circumstances. Okay. So the corresponding stationary distributions can be termed as equilibrium distributions, and the corresponding stationary distribution is termed as equilibrium distribution, equilibrium distribution with probabilities denoted by P equilibrium, and this will result into a compact result, and the result is the compact formula P equilibrium of K is equal to 1 plus L equal to 1, L not equal to K, N W of L given K, and W of K given L, and its inverse. So let's say give this equation or equation number 14. This is equation number 15. Okay, so we sort of discussed these things in great detail. Now what we will do, will coming into the end of this portion, where I will talk about the Fokker-Planck equations, and I will talk about different few stochastic processes, like uh, you know uh, there are different processes you can talk about. I can talk about other processes because I will not go into the details there, but because that will be more thing. But I will talk about different, Woodstein, Uhlenbeck, and this kind of processes that will be much more interesting to say. Okay, so then we'll stop here and we'll continue our discussion in the next class.